What I want to do now is talk about some of the calculus involved with vector valued functions. So let's do this. As an introduction, let's consider a function y equals x squared. And let's suppose that I want to come up with a parameterization, I should say, for that particular function on the interval from -4 to 4. Let's suppose I want that. And let's suppose further that with this parameterization, I want the orientation to be, I want it to trace from left to right. In other words, I want it to do like this. Okay, so I want to represent that curve as a vector valued function. So one of the things I could do is I can say, well, just let x be t, and then y is t squared. So now I have this vector valued function. I can just say, well, this is t and this is t squared. There, now we have a vector valued function. And if I want the t to go from -4 to 4, I'll just say that. T goes from -4 to 4, right? So that's what t is here. Up there, y equals x squared, that was what x, the range for x, but we just let x be t. So here we have a vector valued function that models this curve, okay? So this particular vector valued function will give us a sketch that looks like this. Now, what I want to do is I want to talk about the derivative of this vector valued function. In other words, I want to talk about r prime of t, or, you know, the derivative of the vector valued function, that notation. Nothing new about the notation here. Well, what we're going to find is, and I'll illustrate this in a minute, that just involves taking the derivative of each component of this vector valued function. Remember, you think of a vector valued function as a package of functions. It has a function for the horizontal component, in this case and for the vertical component. Now this is just 2 dimensions. So if we had the third dimension, we would have that component as also. But you just look upon it as a package of functions. So the derivative of t is 1, and the derivative of t squared is 2t. See? All I do is just take the derivative of each component with respect to t. Now, let's suppose that I want to find the derivative evaluated at 2. Let's see what that would look like. That would be, the 1 doesn't change, but then 2 times 2 is 4. So I get this vector, 1, 4. Now I want to go back and look here. Remember, for the vector valued function, if we wanted to put in the 2 into this original, or into this right here. Whoops, let me go back. Okay, let's suppose I wanted to just plot the point when t is equal to 2. Well, I would do r of 2, and I would get the point 2, 4. I would get the vector 2, 4. And notice that if I plotted that, I would start here at the origin, and I would go over 2 and 1, 2, 3, 4. And there's the point on the curve. Now remember, the vector valued function, if you look at the curves, the graph like this, that represents the terminal point of all these little vectors. And we always plot those vectors, when we find something like this, r of 2, we always start at the origin. And the curve is just the collection of those terminal points of the vector. Now, what about this though? This one, I keep using that the vector when I need it to be back at the pen. So what about that? Well, let's plot that. So I want to come over here and I'm going to get a different vector. I guess maybe I'll make it a blue or let's say purple. There we go. And I want to plot that vector. Now notice I'm just going to plot that vector 1, 4. So I go over 1 and up 1, 2, 3, 4. Now there's my derivative right there. There's my derivative vector. But generally, we're not going to leave it right there. When I'm talking about the derivative, I'm usually not going to have it coming from the origin. But this is the vector, right? That's the derivative vector. But here's what I want to do. I want to take that vector, and without changing its direction, magnitude, or anything, I'm going to move it over and put it at the terminal point of this vector. In other words, we've got the vector 2, 4, and the derivative is 1, 4. The way I'm going to represent the derivative is make the initial point of this derivative, make the initial point right here of that vector. I'm going to make the initial point the terminal point up here. Okay? So this vector, if I'm plotting it, initial point at the terminal point of the function value vector, and then it goes off like that. So there's what the derivative looks like, or how we can represent it graphically. And the reason we do that is so that it gives an idea, that's the slope of the tangent. This vector right here is parallel to the tangent vector, or the tangent line for that curve. So this way makes it very clear that we're talking about the derivative. Now we could talk about the second derivative. So let's take a look at that and see what that would look like. So if we're talking about the second derivative, okay, here we go. R double prime of t. Well, remember the first derivative was 1 comma 2t, so this would be 0 and 2. Okay, 0 and 2. So we could talk about plotting that vector. So let's take a look at that one. Let me do it in the yellow. Okay, so this one goes 0 and 2. So that would be what the vector looks like if we started it from the origin. Okay, 0, 2. But we could put it up here at this point of tangency, and there's what it would look like. Okay, so a lot of times you'll see it that way. So this kind of gives you an overview about the differentiation involved. Okay, so you think of a vector valued function as a package of functions. The derivative is just the derivative of each of those functions in the package. So let's look at that a little more rigorously. Let's suppose that we have a vector valued function here. And in fact, it's f of t I plus g of t j plus h of t k. Okay, so a vector valued function. And we want to talk about the derivative. Now, look, remember, the derivative is a limit. So we could say the limit as delta t goes to 0 of r of t plus delta t minus r of t all over delta t. Remember, that's the definition of a derivative. So let's see if that is indeed us just taking the components of the derivative of each component, the I component, the j, and the k. Well, let's see. So let's put this in and see what we get. Well, we get f of x plus delta t I, plus g. And I'll tell you what, let's give myself a little more room. Let's walk down here. So this would be this. It would be f of, and let me put in the limit. Okay. Okay. So here we go. We got f of t plus delta t I plus g t plus delta t j plus h t plus delta t. Okay. Minus all these things. F of t I minus g of t j, okay, minus h of t, k, all over delta t. And I guess over here I left off the k. There we go. Now let's put everything together and see what we've got. Okay, so what I'm going to do is I'm going to do a little bit of grouping. I said everything. I'm going to group the f's together. So let's see what we've got here. I've got f of t plus delta t minus f of t over delta t I. See? So I've grouped the f's together. Plus the limit, delta t goes to 0, of g of t plus delta t minus g of t over delta t. Okay, got that. And then finally, the grand finale, I've got the limit as delta t goes to 0 of h of t plus delta t minus h of t over delta t. And then there's I left off the j, and here I got to remember the k. Can't leave those off. Okay, so now look what we have. And if you think about it, if you just look and remember the definition of a derivative, this first part is f prime of t, I. The second part is g prime of t, j. I mean, that's just definition of a derivative. That's just the difference quotient. And then finally on the end, you've got h prime of t, k. There. So you can see, yeah, we're just differentiating component by component. That's all we're doing. So we might have this vector valued function here. Let's suppose that we have t squared sine t and e to the 2t. Suppose we have that vector valued function and we want to talk about the derivative. Well, that's just going to be each component. So the derivative of t squared is 2t. The derivative of sine t is cosine t. And the derivative of e to the 2t is 2e to the 2t. There you have it. And there's your derivative. Now, just like when you first learned about derivatives, just real functions, you learn their properties like the product rule, the quotient rule, and that sort of thing. Well, the same is true for vector valued functions. So we have to think about some of those properties. Now, I want to start off by thinking about the derivative of a dot product. This is something we've not encountered before, the derivative of a dot product. But what you need to do is you need to think product rule, because you're familiar with that, and this follows that. Because what you're going to do is you're going to take the first times our dot, the derivative of the second, dot instead of times, right? Plus the derivative of the first, dot the second. See? So it's the product rule, right? The first times the derivative of the second plus, not times, the first dot the derivative of the second plus the derivative of the first dot the second. So the vocabulary there, I have to be careful. I'm dealing with vectors. So this is one of the first properties we want to look at. And what I want to do is I want to verify that property for you and just show you how that process goes. Now, for simplicity's sake, I'm going to define my vector u to be f1, g1. In other words, I'm not going to go 3 dimensions or 4 dimensions or n dimensions, but you will be able to see, yeah, I could expand this for however many dimensions. And then I'm going to let vector v be f2, g2. Okay, now let's first of all find the dot product, u dot v. Well, that's f1, f2 plus g1, g2. That's the dot product. And now Let's go ahead and take the derivative of that, and we'll show that that derivative is just this right here. Okay, so nothing wrong with what we've done so far. So now I do the derivative with respect to t of this business here. And now, see, now we're not even dealing with vectors. We're just dealing with some functions. Started to make a vector thing. We'll close. There we go. We just want to find the derivative of that. And we know how to do this. This is just the product rule a couple of times. So we've got the first times the derivative of the second plus the derivative of the first times the second. Okay, that takes care of those f's. Now let's look at the g's. So we've got g1, g2 prime, see, derivative of the second times the first plus the derivative of the first times the second. There we have it. Now, let's see if we can, let's think about this a second. Let's just think about the derivative of u, okay, which is going to be, it's going to be f1 prime g1 prime, okay? And then the derivative of v, which is going to be f2 prime g2 prime, okay? So there's that. There's u prime v prime, okay? Now, first of all, so let's think about this. Let's do this. Now, what I want to do is I want to calculate u dot v prime. Okay, so here is u dot v prime. U dot v prime. Okay, so here it goes. F1 G1, and here's v prime. F prime 2 G prime 2. Okay, now let's do the dot product. Here it goes. F1 F2 prime plus G1 G2 prime. Okay, that's u dot v prime. Now let's do this. Let's do u prime v. U prime dot v. Okay, let's see what that looks like. So here we go. U prime, that's going to be F1 prime G1 prime dot v, which is F2 G2. Now let's see what that looks like. So here we go. We got F1 prime F2 plus G1 prime G2. Now, remember, we're wanting these two things added together, this and this, to equal this. We want to show that those are the same. So let's rewrite it up here. Now notice, I've got, if I add these two things together, I've got F1, F2 prime. Okay, so here's F1, F2 prime. Okay, got that. And then I've got F1 prime, F2. Okay, got that. And then for the G's, I've got G1 prime, G2. Actually, G1, G2 prime, sorry. And then finally, this one over here, which is G1 prime, G2. There. And that's exactly what we wanted to show. So we verified. So to verify this, notice all I did was I picked general vectors, and then I just, went through and did the work and showed that, yeah, they're equal. Whether or not we do this or this, we get the same result. Now, there are other properties of these vectors. For example, let's suppose we have the cross product. Well, this is going to be, just like you would think. What we're going to do is we're going to say, okay, this is going to be U cross V prime plus U prime cross V. So we've looked at the derivative of a dot product, derivative of a cross product of two vector valued functions. Now just think though, sometimes you might have a situation where you have a non-vector valued function, let's call it W, and then you have a vector valued function. Well, you still go about this the same way. You've got W of t times V prime of t. So you're still using the product rule, plus W prime of t V of t. Yeah. So these properties are what you would think they would be. Now, let's suppose you have a composite function situation where you have R of W of t. Well, and this is a vector, of course. Well, then you would say, okay, so this is going to be R prime of W of t times W prime of t. There it goes. So there are a few properties. This is not an exhaustive list, but that's a few of them.